Hello, and welcome to another video for Astronomy 102. Our topic today is the Moon. The Moon is Earth's only natural satellite, and is unique in the solar system in that it is relatively large compared to the mass of its parent planet. We will start by characterizing the Moon's orbit around the Earth, and the consequent relative motion of the Moon against background stars. When we think of the Moon orbiting the Earth, our minds perhaps come up with a picture somewhat like this one here. But if I were to draw this to scale, a more accurate representation would be like this, which makes the Moon seem very far away, and makes the space missions of the 60s and 70s an even more impressive feat. I am always amazed when I think that we sent humans to walk on another world. As the Moon orbits the Earth about once a month, it also changes its appearance drastically, going from almost invisible to a sliver of a crescent, then growing until a nice round full moon appears before it, reverses the process until it disappears again from sight. We will discuss the origin of these differences and understand where and when to look for the Moon at each phase of the cycle. Finally, we will discuss the phenomena of solar and lunar eclipses, which are rare and wonderful events that happen when certain arrangements of the Sun, Moon, and Earth occur. After listening to this lecture, you will be able to understand why certain eclipses look like this, while others never quite achieve totality and look more like a ring in the sky. You'll also understand why, in the exact moment of a total lunar eclipse, the Moon, instead of disappearing or turning dark, turns instead an eerie blood-red color, which frightened people for centuries, and maybe still does now, before its cause was understood. You're very lucky because there will be a total lunar eclipse on April 15th this semester, and hopefully we will be able to observe this event at our star party that night. The Moon is about a quarter of the size of the Earth, and it's approximately 2,000 miles in diameter to the 8,000 miles of the Earth. Because it is smaller and less massive, you would weigh a lot less on its surface, only about a sixth of what you weigh on Earth. If you weighed only 1/6 of what you currently weigh, you could bunny hop down a rocky slope.
This is the best way for me to travel, uphill or downhill. But then, like this, two-legged hop, that means and on level ground I can skip. I don't like that loping thing. Oh, the loping's the only way to go. Checkpoint. See, when I'm on level ground, I can skip.
Or you might have trouble figuring out how to stand up.
No. Dadgummit. Jack Schmidt having a few problems.
The Moon revolves around the Earth in an orbit that's close to circular, at an average distance of 238,857 miles. That looks like a very precise number, and in fact, we know the distance to the Moon to a few centimeters. The distance varies by a lot because its orbit is not perfectly circular. Sometimes it's closer, at its closest, 225,622 miles, and sometimes further, at its farthest, 252,088 miles. How do we know these distances so accurately? Astronomers actually beam lasers from the Earth, aimed at mirrors on the Moon left by the Apollo missions. This is a picture of the Lunar Laser Ranging Facility at McDonald Observatory in Texas. The laser beam you see there is headed for the Moon, where it must hit a mirror left behind by the astronauts that's only a few feet wide. Now this is quite the feat. Once the laser hits the mirror, it gets bounced back at Earth, and we can measure the time it takes for the laser to reach the Moon and back, and therefore measure the distance to extreme accuracy. In fact, by using this method, we've established that the Moon's orbit is actually getting wider. In other words, the distance between the Earth and the Moon is increasing very slowly, about 3 centimeters a year. The Moon completes one full orbit around the Earth every 27.3 days, which means that, like the Sun, it moves against the background stars. Which way does it orbit? Remember your mnemonic from the first class. The moon revolves around the Earth counterclockwise if you are looking at the Earth-Moon system from above the North Pole. Notice the cap? So in this case, your thumb points along the North Pole of the Earth, and your fingers curl in the direction of the orbit of the moon. It's no coincidence that the moon revolves around the Earth in the same direction as the Earth rotates. This is also the same direction that the Earth revolves around the Sun, and in fact all planets revolve in this direction. The entire solar system, the Sun, the planets, the moons, and asteroids, all formed from a collapsing giant cloud. As this cloud collapses under gravity, it picks up angular momentum, much like an ice skater bringing their arms in to spin up faster and faster. You can also try this in a spinning chair. Start with your arms wide and rotate, and then bring them in very fast, and you'll see how your speed goes up by a lot. This extra spin made the solar system flatten out like a pancake to make a very thin plane, where most everything is spinning in the same direction. There are anomalies. Planets have tilts, like the Earth, and some, like Venus, even spin in the opposite direction. Like Kate mentioned in the previous lecture, astronomers believe that these are the results of collisions in the early solar system. But back to the moon and its orbit. Let me bring in some stars as reference points. But remember, in reality, these stars are much, much further away. In fact, the closest star is 25 trillion miles away. Compare that to the 238,000 miles that the moon is at, and all of a sudden, that doesn't seem quite so far away. The moon, as we were saying, revolves counterclockwise around the Earth, and its relatively short orbital period causes it to move quite rapidly against the background stars, which are fixed. As the Earth moves around, the stars against which we see it from the Earth are going to change quite rapidly. You'll measure exactly how rapidly in your observing assignments. As the moon orbits the Earth, it goes through very marked changes in appearance. This made it particularly easy to mark time. Calendars based on the moon's appearance go back to antiquity, and it is the basis of the month. 30 days is approximately one lunar orbit. The moon goes from full, wanes into new, and waxes back into full in 1 month. You can see from this great yearly lunar calendar for the year 2013 that it isn't a perfect match. The phases of the moon don't quite line up from month to month, so you don't always get a full moon on the same day of the month, which is a shame really. It would be very practical. Although perhaps not all that surprising, given that months themselves have different lengths. The names of each phase are represented in this diagram here. If we start at new moon and move, remember, counterclockwise, we see that the moon's phase increases or waxes to a thin waxing crescent before going on to a first quarter where half of it is illuminated as seen from Earth, to a waxing gibbous where it's somewhere in between first quarter and full moon, and then full moon where the whole face as seen from the Earth is illuminated. We then start decreasing, going to waning gibbous, where not quite all of the surface of the moon is illuminated, to last quarter, where only the left half side of the moon, as we see it, is illuminated, down to the waning crescent, where we only get a thin sliver on the left, and back to new moon. In order to understand why we see different phases when the moon is in a different place in its orbit, we first need to know that half of the moon, the half that's facing the sun, is always illuminated, and the other half is always dark. In fact, any spherical object in the solar system, be it a moon or a planet, will always be divided in half. The half that faces the sun is in light, the half that faces away is in shadow. This is always the case. It's a simple matter of illumination, and you can test this by holding up any spherical object up to a source of light in an otherwise dark room. The appearance of the different phases on the Moon is due to the different Earth-Moon-Sun configurations during the Moon's orbit, and how much of the illuminated half of the Moon we are able to see from Earth. Remember, half of the Moon is always illuminated. It's just that sometimes we can't see it from where we are on Earth. So let's go carefully through this diagram here, and we'll see clearly how this happens. At new moon, if we draw a red line across that divides the Moon into the part that we can see from Earth and the part that we can't see from Earth that's facing away, we see that the part that's facing the Earth is completely in shadow, and that's why we get a new moon, which is completely dark. Now, revolving counterclockwise, we wax into a waxing crescent. Again, we divide the Moon into the half that's seen from Earth and the half that can't be seen from Earth. And we note that of the half that we can see from Earth, there's a small sliver on the right-hand side that receives illumination from the Sun, and that's why we see a waxing crescent. If we move forward to first quarter, again, the half of the Moon that we can see from the Earth, we see that the right-hand side of the Moon is fully illuminated by the Sun, but the left-hand side, the left half, is in darkness, which is why we see half of the Moon illuminated in that way. At waxing gibbous, most of the face is illuminated except for a small sliver on the left-hand side, which is in darkness, and that's why we see waxing gibbous. And then at full moon, we see that the entire half of the Moon that we can see from Earth is bathed in sunlight, which means that we see a full moon, with no part of the Moon in darkness. Moving forward, we go to waning gibbous, where the right side of the Moon is a little bit in darkness, but most of it is still illuminated. Then the last quarter, where the right half of the Moon, as seen from Earth, is in darkness, but the left half is illuminated. And then to waning crescent, where only again a little sliver of light is along the left side of the Moon. Now the phases of the Moon occur because the Moon moves with respect to the Sun's direction as it orbits around the Earth. This means that the position of the Moon with respect to the Sun on the sky, as seen from an observer standing on Earth, is going to change throughout the month. And it also means that if you know what phase the Moon is at, you can know when and where to look for it on the night sky. Before we get to that, though, let me do a quick review of how to tell time depending on where you are on the Earth's surface. So here we are on the surface of the Earth, and as we mentioned before, half of the Earth is illuminated and half is in darkness. The half that is illuminated is the half that faces the Sun. We've placed our observer on the surface of the Earth, and you can imagine that he's standing at the equator and that the North Pole is coming straight out of the video towards you. If the observer is at the equator and the Sun is straight ahead, then you know that it must be around noontime. Remember, these times are approximate, but you expect that at noon the Sun is highest on the sky. We've also labeled the observer's east and west horizon. Now remember, we're going to rotate counterclockwise so that the observer and the eastern and western horizon move. Of course, the Earth has rotated, but the half that's illuminated hasn't, because it's always facing the Sun. So at this point, for this observer, he sees the Sun lower on the sky and getting closer to the western horizon. That's around 3 p.m. 3 hours later, the observer is now at the border between light and darkness. This is what happens at sunset, when the Sun has just dipped below the western horizon. 3 hours later, we find ourselves at 9 p.m. 3 hours later, we're at midnight. The Sun is directly opposite us from where the observer is standing, so it's directly under his feet, beneath the Earth. 3 hours later, we're at 3 a.m., and 3 hours later, we're again crossing the threshold from darkness into light, and the Sun appears to rise above the eastern horizon. At 9 a.m., the sun is a little bit higher above the eastern horizon. As we move forward towards noon, the sun is once again straight overhead. Now let's introduce the moon into this diagram. If we want to represent the moon at full moon phase, we place it where the face that we see from the Earth is fully illuminated by the sun, so directly opposite the sun from the Earth. This is where we see a full moon. Now let's place our observer back at noon again, and notice that when the sun is directly overhead, the moon will be nowhere to be seen. It'll be straight under our feet. As time goes by, at 3 p.m., the sun dips again towards the western horizon, and we still do not see a moon. But at sunset, exactly at the moment that the sun dips below the western horizon, the moon will rise above the eastern horizon in all its full moon glory. At 9 p.m., it'll be low on the eastern sky. At midnight, it'll be straight overhead, a bright full moon above your head, whereas the sun is right below your feet. At 3 a.m., the moon moves towards the western horizon, and at 6 a.m., the moon sets below the western horizon just as the sun rises in the east. At 9 a.m., the sun is again higher on the eastern horizon, and the moon is below the horizon and not visible. Let's think now of a different phase. Let's move the moon up to last quarter phase. So now, if we look at what half of the moon can be seen from Earth, we see that the left side of the moon is in light, is bathed by sunlight, but the right half of the moon is in darkness, and so we see a last quarter moon. If we bring back the observer, at noon again, we notice that the moon is below the horizon. As we advance in time, this last quarter moon cannot be seen at 3 p.m., nor at 6 p.m., nor at 9 p.m., but at midnight it appears to rise above the eastern horizon, so that at 3 a.m. it's a ways above the eastern horizon, and at 6 a.m. it's directly overhead. Now at 6 a.m. is the time when the sun rises as well, so now you see that as the sun is rising, the last quarter moon is directly above your head. Interesting, at 9 a.m., the sun is well above the eastern horizon, climbing towards its position at noon, but the moon is still well above the western horizon, so it can be easily seen in the daytime. We can do this for all the different phases of the moon, and I encourage you to try to sketch out these diagrams at home, since one of the main goals of this class, of this particular lecture, is for you to be able to predict where the moon will be and what time it will rise and set depending on its phase. So this kind of diagram is very important for you to become familiar and comfortable with. We will practice this more during lab in class. I want to go back to talk about the moon's orbit again briefly. This picture I showed you before is of the moon in its different phases. Now you might notice something funny. Even though the degree of illumination changes as the phases change, the face of the moon remains exactly the same, with the same features in the same place throughout the entire cycle. We can follow the small crater as the moon changes through the different phases. You might have noticed this in your own observations of the moon. The fact is, we always see the same side of the moon from Earth, and in fact people have called this the face on the moon. How can this be? We saw before that our view of the moon changes drastically as the moon travels through its orbit. We can visualize what's happening with a simple schematic. I'm representing a specific location on the moon by this red dot, and I'm going to now move it throughout its orbit. Now, if the moon itself did not rotate, but only revolve around the Earth, then at this position of its orbit, we would be able to see the red dot clearly. But a little while later, the red dot would be on the edge between what's visible and what's not visible from Earth, and at this part of the orbit, it would be completely invisible from the Earth. Half an orbit later, it would be on the exact opposite side of the Moon. So this is obviously not what's going on in the Earth-Moon system. What's happening is that as the Moon revolves around the Earth, it's also rotating, so that as it moves along its orbit, it rotates just enough so that that little red dot is always pointing towards the Earth. You see that half an orbit later, the red dot is still facing exactly towards Earth, and the Moon has essentially rotated half a way around, so 180 degrees. We can continue seeing this as the Moon rotates. This is called synchronous rotation. The Moon rotates, and it does one rotation every time it does one revolution around the orbit, around the Earth. So one rotational period equals one revolution period. So we always see the same side of the Moon. For this reason, the far or dark side of the Moon, as people usually call it, was a very mysterious place to humans for most of history. It was only with the launch of the space program in the 60s that we could finally look at what was on the other side of the Moon. Are you curious? Some people might think that they'll find little alien colonies on the other side. More skeptical minds might think that it's just going to look exactly the same as the face of the Moon that we can see. Are you ready? This is what the dark side of the Moon looks like. It actually looks very different from the side of the Moon that we can see. We can compare it here with the usual friendly Moon that we're used to seeing, and we can see that the dark side of the Moon has many more small craters and a lot fewer of these giant basalt seas that are called marias, these dark patches of smooth surface. The reasons for that are quite interesting, but you'll have to take Astronomy 101 to find those answers. One last thing before we move on to eclipses. People often refer to the far side of the Moon as the dark side, but from what we've learned in this lecture, you now know that it is not always dark on the dark side of the Moon. In fact, at new moon, it is fully illuminated. Really, it gets as much light as the near side of the Moon, just at opposite times of the month. Eclipses happen when an object moves in front of the Sun and is said to occult it, which means to block from view. The Moon orbits the Earth, which means that sometimes it is between the Earth and Sun in new moon phase, and sometimes the Earth is between the Moon and the Sun, the full moon phase. At either of these times, if the alignment of all three objects, the Sun, the Moon, and the Earth, is perfect, one body can block the other and cause an eclipse. During a solar eclipse, the Moon appears to travel in front of the Sun. First part of the Sun gets occulted, and eventually, during a total eclipse, the Moon completely covers the solar disk. It's like someone turns off the lights for a brief minute. The sky goes dark, the birds stop singing, and the stars come out. This moment only lasts a few minutes before the Moon moves away again. Now, the first amazing thing you should notice about eclipses is that the size of the Moon and Sun on the sky are very, very similar. They are both about 1/2 degree on the sky, which is a little less than the width of your pinky at arm's length. Yes, I know that seems too small compared to how big we remember the Moon on the sky, but test it out next time you are out at night. Now we know the Moon and the Sun have very different actual sizes, so how can this be? Examples of this kind of illusion abound. Here we have a picture of a jetliner in front of the Moon. Same apparent size, more or less, even though the Moon is 2,000 miles, and the plane is, well, maybe a 1/20th of a mile if we're being generous. Another great example of this illusion is this picture of a palm tree in front of a solar eclipse, or in the bottom, a man eating the setting sun. What's going on here? The common factor is that all these things, the plane, the palm trees, the man, are much, much closer to the camera than the background object. Where this man is 2 feet away, the Sun is 93 million miles away, so it appears edible. The same is true for the moon and the sun. The sun is much bigger than the moon. Its diameter is 864,000 miles versus the 2,000 miles that make up the diameter of the moon. This means it's about 400 times larger. On the other hand, the moon is much closer to us than the sun, 240,000 miles versus the 93 million miles to the sun, which means that the sun is about 400 times farther. You might be seeing where this is going. Remember from class that in order to measure the apparent size of an object, we actually measure the angle that it spans on the sky. And the shorter the distance to the object, the larger the angle. The larger the object, the larger the angle. Makes sense. So if you're ready for the first equation of the class, I'm going to tell you that the small angle formula, which gives you the apparent size or angle on the sky of an object, is equal to the size of the object divided by the distance to the object. This is called the small angle formula because it only applies in the case where the angle is small, and half a degree we can consider to be small. So if we apply the small angular formula, we see that the apparent size of the sun is going to be the size of the sun divided by the distance of the sun. Now we just said that the size of the sun is about 400 times the size of the moon, and that the distance of the sun is about 400 times the distance of the moon. We can cancel these two factors out and say that the apparent size of the sun is equal to the size of the moon divided by the distance of the moon, and then see that of course this is just equal to the apparent size of the moon. So that's how we can tell that the size of the sun and the size of the moon apparent on the sky are the same, even though they're at such different distances and they have such different sizes. This is a great coincidence, and it didn't have to be this way. For example, Mars' moons are so small that Mars only ever has partial eclipses. Jupiter, on the other hand, has large moons, and the sun is so much further away that total eclipses on Jupiter are very common. This is a wonderful picture of the planet Jupiter and 3 of its moons, and you can see that each of those 3 moons is causing a total solar eclipse on the surface of Jupiter. In fact, in the future, we probably won't have total solar eclipses anymore. Remember that the Earth-Moon distance is increasing very slowly. In less than 1 billion years, total solar eclipses will be a thing of the past, which will be a shame if anyone's still around to look up at the sky. But for now we have some time to enjoy this phenomenon. Total solar eclipses are quite rare and can only be seen from a very small area of the globe. This is a map showing all of the solar eclipses in a span of about 20 years, and it shows the path of the solar eclipse on the surface of the Earth. You can see that those paths are quite narrow and that they're not very common, and in fact, many times, they happen just over the ocean. People travel very far to see this spectacular phenomenon, sometimes even to the middle of the ocean. However, in August 2017, just a few years from now, there will be a total solar eclipse that will pass right through the continental United States, which will make it a unique opportunity for us to witness one of these amazing events. You'll notice that the path of the eclipse is quite narrow. This is called the path of totality, the area of the Earth from which a total eclipse can be seen, and it is at most 167 miles wide. You can see this here in this picture taken from space of the Earth during a total solar eclipse. Only a very small part of the Earth is in the shadow of the moon, and only the very center of the shadow is completely dark. The rest of the shadow is called the penumbra. From these locations on Earth, the sun appears only partly covered because the alignment between Earth and moon and sun isn't perfect. This is a diagram showing you how this works. The umbra is the part of deepest shadow, and that's only a very small spot on Earth. The penumbra is a much larger area where people will only be able to observe a partial eclipse. So what happens during a lunar eclipse? Lunar eclipses only occur during full moon because that's when the alignment between sun, earth, and moon can occur. Remember, at full moon, the moon and sun are exactly opposite on the sky, one rises as the other sets. During a lunar eclipse, from the perspective of an observer on the moon, the Earth covers the sun, just like the moon did during a solar eclipse. It is important to remember that during a lunar eclipse, it is actually the Earth that is occulting the sun and blocking sunlight from reaching the moon. The Earth is quite a bit larger than the moon, though, so you'll notice that in this picture taken by a Japanese lunar probe, the Earth's apparent size is much larger than the sun's. The Earth's shadow is cast on the moon, just like the moon's shadow was cast on Earth. But the Earth is quite a bit larger than the moon, so its shadow is much larger. In comparison with a solar eclipse, the totality path is much wider and in fact can engulf the whole moon. This means lunar eclipses last a lot longer, hours versus minutes, and this is also the reason why total lunar eclipses are much more common than total solar eclipses. Lunar eclipses can also be seen from anywhere on Earth, which increases your chances of seeing one. In fact, there will be a lunar eclipse on April 15th. I hope you will all be able to observe it, and we will be making some measurements to try to determine the size of the Earth's shadow, and therefore determine the size of the Earth, just by watching the eclipse, so stay tuned. When you observe a total lunar eclipse, first you see the Earth's shadow moving in, and making a partial eclipse. But, at the moment when the eclipse is total, you might expect the moon to turn dark and invisible. Instead, it often becomes blood red. This doesn't happen in a solar eclipse. The ground doesn't turn orange or red, it just goes dark. Can you think of why this would be? It's actually your old friend, the atmosphere again. Remember back to that thin slice of gaseous atmosphere covering our rocky planet Earth? You can actually see it on this picture of the Earth during a lunar eclipse. A thin layer coating the solid surface. Sunlight is blocked by the solid Earth, but is transmitted through the atmosphere, so some light gets through. However, remember how the blue light kept getting deflected and scattered around? The red light is the only one that makes it through the atmosphere, so the red light from the sun bathes the lunar surface, making it look like a bad omen or a beautiful sight, depending on your individual sensibilities. But wait a minute, you say. If total eclipses happen when the moon is in between the Earth and the sun, at new moon, and lunar eclipses happen when the Earth is in between the sun and the moon, at full moon, then why don't eclipses happen every month? Twice a month, even? That's a very good question. The answer is they would, if the moon's orbit were perfectly aligned with the Earth's orbit around the sun. Instead, the moon's orbit is actually tilted by 5 degrees relative to the plane of the ecliptic, or the plane of the sun, which means that we only experience eclipses a couple of times a year when the two line up. Incidentally, that's where the name ecliptic comes from, the plane where eclipses can occur. Okay, one more question. You said, in the beginning, the moon's orbit wasn't circular. Okay, one more question. I said in the beginning, the moon's orbit isn't perfectly circular, so that the distance to the moon varies along its orbit by almost 30,000 miles. Won't that affect its apparent size? Indeed it will. When the moon is closest to the Earth, it actually appears a little larger than the sun on the sky, and when it's farthest, it appears a little smaller. This is often called in the media by names like supermoon and micromoon, and they try to really drum up the excitement. But really, all you're seeing is the moon at different places in its orbit, where it's coming closer to the Earth and going further away. The ellipticity of the Earth's orbit around the sun also changes the sun's apparent size, but not by very much, since the orbit is so close to circular. Anyway, this means that there are times when the alignment between the sun, moon, and Earth is perfect, but the moon is too far from the Earth and too small in the sky. In that case, we get an equally beautiful, if perhaps less spectacular, annular eclipse. I'm going to leave you with a summary of the important concepts we covered in this video. See you next time.